The human heart has the ability to beat independently without any nervous input. This is because it has something called a cardiac conduction system. This begins with the pacemaker. The pacemaker keeps the pace of the heart. Without any input from the nervous system, the heart will beat about 72 beats per minute. So, this is made possible by electrical impulses that travel throughout the heart and making the heart beat synchronously. So, let's go over these. The first step is the pacemaker. The pacemaker is otherwise known as the SA node, and from there, the information goes to the AV node or the atrioventricular node, and then to the AV bundle, followed by the bundle branches, number 4. Number 5 are the Purkinje fibers. Let's go over these again. So first we have the pacemaker, which is the sinoatrial node, otherwise known as the SA node for short. This is very important because if something is wrong with the SA node, then the entire heartbeat will be irregular. So next we have the AV node, number 2, which is the atrioventricular node, followed by the AV bundle, which is number 3. And then we have the bundle branches that take the information to the ventricles and all through the heart via the Purkinje fibers, which is number 5. Altogether, we call this the cardiac conduction system. If there are any irregularities in the cardiac conduction system, it will be seen on the ECG, producing irregular and unusual heartbeats. In order to understand the electrical impulses that are generated at the SA node, we need to understand how action potentials are generated at the SA node. So we call this a nodal action potential. Here's the graph. The x-axis we have time in seconds, and in the y-axis we have membrane voltage in millivolts. Let's make a few important points. Minus 60 millivolts, minus 40 millivolts, 0 millivolts, and plus 30 millivolts. The minus 40 millivolts is important because it is the threshold voltage. If you remember, the threshold voltage is the minimum voltage needed to trigger an action potential. At minus 60 millivolts, voltage-gated sodium channels open and sodium flows in, causing a depolarization. At minus 40, voltage-gated calcium channels open, and at plus 30, voltage-gated potassium channels open, producing an action potential. From minus 60 to minus 40, we call it the pacemaker potential. This is in the place of a resting membrane potential, which the heart does not have. It has a pacemaker potential in the SA node. So the action potential has a depolarization phase and a repolarization phase. The depolarization phase is caused by calcium, and the repolarization phase is caused by potassium. So let's review this. The pacemaker potential is caused by slow sodium inflow, depolarization by fast calcium inflow, and repolarization by fast potassium outflow. Together we have an action potential. Let's review what we just learned about the formation of an electrical impulse at the SA node. The first stage is the formation of the pacemaker potential. At minus 60 millivolts, voltage-gated sodium channels open and sodium flows in. So there is an inflow of sodium. So let's repeat that. At minus 60 millivolts, voltage-gated sodium channels open. There is a slow sodium inflow. Sodium inflow brings in positive charges, and so there is a slow depolarization. the voltage now reaches minus 40 millivolts. The range of voltage between minus 60 millivolts and minus 40 millivolts is called the pacemaker potential. Remember, this is different from the resting membrane potential in the neuron because the SA node does not have a resting membrane potential. It never rests. It only keeps the pace. So we have a pacemaker potential. The next phase is the depolarization phase of the action potential. This is brought about by the threshold voltage. We remember that the threshold voltage is the minimum voltage needed to trigger an action potential. So at minus 40 millivolts, voltage-gated calcium channels open. Fast calcium inflow occurs because if you remember, there is more calcium outside the cell, so there is always a calcium inflow. Calcium inflow brings in positive charges, so this causes a depolarization, a rapid depolarization that makes the voltage go up all the way to plus 30 millivolts. So from minus 40 millivolts to plus 30 millivolts, we call it the depolarization phase of the action potential. It is the rising phase when the voltage increases. The third phase is the repolarization phase of the action potential. This is brought about by the opening of potassium channels. Potassium channels usually open around 0 millivolts. In this case, the depolarization is so fast that it passes the 0 millivolts and reaches plus 30 very rapidly. So around plus 30 millivolts, potassium channels open. These are voltage-gated potassium channels, and this causes potassium to leave the cell. Remember, there is always more potassium inside the SA node cells, so potassium leaves the cell. So we have a fast potassium outflow. This causes positive charges to leave the cell, resulting in a repolarization, and this repolarization is also rapid and reaches minus 60 millivolts so that the cycle can now repeat. The voltage from plus 30 millivolts to minus 60 millivolts, we call that the repolarization phase of the action potential.